right, let's dive right in. Good morning. Welcome back to my stream. Let's switch over here and figure out what I've been thinking about. So we finished up, or I thought we finished up 25.3, which is the up value stuff, up value objects, as it's called here. But when I was looking over the code, not here, enclosures, yeah. I realized that this modify thing is modifying the up value, is changing the ref cell, it's changing the entry in the vector, but it needs to be changing the entry in the stack. And most of the time it's okay that we change the entry in the vector because we just grab the up value. If we look at, let's see, let's take a look at this devious example. It's supposed to print create inner closure, return from outer, and then value. And that works, right? Cargo, run, alt features. Because we're not doing any assignments in here, so everything sort of just does the right thing. But there was one test, yeah. So that works correctly. And this one says run this and it correctly prints outside. Which one was the one we did? Or what was the file we did that in? Try this. Cargo run. No default features. This. And it correctly prints outside. This is not testing any assignment thing. So anytime we modify this line here, this is not testing this line here, which is our which is the way we implemented this. See, in set up value, I call modify. So let's take a look at set up value. Set up value. Yeah, so I'm just calling set up value here to set it on the closure. Right, if we take a look again, the set up value actually goes here. It says grab the closure and call modify to modify the closure's view of it. But the closure should be pointing to through the up value. Where's up value? Here it is. Should be pointing to the stack entry. The entry on the stack. So we need to update the entry on the stack. So we do have one thing. Here it is. It's called assign. Cat assign. One test that does the assign. So we set it to before. The inner changes it to assigned. So now we call inner and we print X, and this should print out assigned. But we're modifying the wrong value. We're modifying the value inside the inner instead of inside the outer, which means we won't get this. So I think if I look at assigned, yeah, the program should print assigned even though the closure assigns to X and the surrounding function accesses it because of values of objects. Okay, so if I cargo run this, and I'll do it with the full debug out. Yeah, see, it's printing before. And if you look at the stack, we pushed before onto the stack. We call this inner function. It has assigned on the stack, and when it pops off the stack here and set up value, it's supposed to pull this assigned off and actually modify this stack entry. Right? That's what this line down here is doing, is actually going to the through the closure, through the up value. The up value points directly into the stack and then modifies it to whatever is on the top of the stack. So it doesn't pop it here. It just copies it into the stack. So this line here, after set up value runs, this should change to assigned. And of course our machinery doesn't do that because, oops, closure. All we're doing is modifying the entry in the up values array. So we need to be able to modify stack variables directly, which means if we look at the VM, this stack can't just be RC values, right? They have to be RC ref cell values, which is going to require quite a bit of refactoring. Right? We need to be able to do this so that we can modify an entry in the stack once we have an index to it. And the reason it has to be an RC is so that we can point to it from either the up values array in the closure or through the stack of the VM itself. So, with this modification in hand, which I think is what we need to do, hopefully that's not the wrong thing to do, because that would be painful to go through this refactoring process. We have to change every place which uses the stack or pushes and pops, right? That too would have to modify to handle this. So let's go through that pain. Let's let the compiler help us do that. So we have 14 errors we need to fix. The first thing is, right, we have to push a new ref cell for the function. Wow, look at this. RC new, ref cell new, value closure, RC new, closure new, RC new. Look how many RCs we're going through here. So the next one is here. So how do we, I guess we can just borrow the ref? I don't know if that's going to cause pain with the bar checker. Yeah, borrow the ref. Capture up value has to return a ref cell value. And the next one is borrow the ref. And we can't print the slot directly anymore because it's going through a ref cell. So we can do this though, slot not borrow. Right, what's next? Oh, get up value has to return the right thing. In fact, all of these need to, right? Set up value needs to have a ref cell value like that. And then there's push and pop, right? Where's push and pop? There's push. Oh, pop. I guess push is okay, right? And peak needs to change, right? And then this can be ref cell view, like that. All right. I'm looking down here at call. It looks like call. So peak is going to have to go borrow. Peak arg count not borrow. Maybe. Well, that's a panic. I don't know what else. Well, let's let the compiler tell us. And now we're up to 22 errors, so we're making it worse. Good. Oh, right, because this getup value needs to return an RC RC ref cell value, which means we need to change the up value as well, right? Yeah, that makes sense. Wow, we have to go through this whole thing. Oops. That still works, right? And then this needs to be ref cell value. This is going to take a while, isn't it? What's the next error? We're passing an RC ref cell value to modify. Right, okay, so this is the code that we actually need to change. This needs to do a borrow mute and change it to ref cell value. And change it actually like this, is my guess. Right, and that way we can actually modify what this is pointing to, I believe. Oh, right, use standard cell, ref cell. We can't do that. Method not found in RC. Oh, because this is an up value. Oh. Okay, so we don't do it this way. We call, because it's an up value, we actually have to call set on it. Like that. And then we'll create a pub set. And it's a ref cell. And it doesn't need to, oh, it needs to take in the value. And then I guess we can just clone it directly in there. Self location dot borrow mute equals value clone, I think. I don't know if that worked. We have to fix all these first. Push up value. So this needs to be ref cell value. Mismatch types, yeah. Push up value. Expected value found. Struct ref cell. Oh, okay. So push up value. Oh, push up value already expects that. RCRF cell value. Deref. We somehow have to shove that value in here. And okay, that's not working either. Expected enum value found reference. Oh, do I have to? Okay. So that means that has to be a value, which means modify. Ooh. Expected value. Borrow. And now no more deref. Okay. Let me go back here now and see if I can get away with this. Oops. This. That seems to work. Okay. That. Well, I'm really glad this cargo check is fast, because otherwise this would be pain. Peak. Peak is RC ref cell value. Oh, so we have to borrow to check to see if it's falsy. And now this all changes. Self pop. Pop should return a. Oh, right. Our globals are values. So our globals be ref cell values? No, we should copy these in, right? So we can say borrow clone here. Let's see if that works. So far, so good. At some point, we're going to hit the borrow checker, though. So self peak. Let me see if we can get rid of this Q now. Borrow clone. Change that to P again. Okay. So pop borrow. Value. Oh, I can't just say borrow here, right? Because it'll. Well, the lifetime thing will complain, right? Borrow. Oh, right now that this is a. Can I get away without having to do any of that? Just say push if I do a borrow clone. Nope. Cannot apply. Oh, because I changed. That's right. I changed it yesterday to the ampersand thing. Okay. All right. This expression has ref cell. Oh, yeah. And if I do this, we're gonna run into lifetime issues. So I'll have to fix that as soon as we get there. Really? Okay. And then this. Oh, it's right. It's an array. Okay, so what is this? Commander thrashed in. Hi, how are you? All right, so these need to pass in ref cell value. not found in the scope. Cell, ref cell. Ben Thrashton says, what kind of languages are you making? What I'm doing is I'm following this crafting interpreters. This is the, I'll paste this into chat. What this is a interpreter for the jlox language that the guy who wrote this book, Bob Nystrom, made up in order to teach people how to make interpreters. But right now I'm learning more about Rust than interpreters. So yeah, this changes to ref cell value. And what he did was he wrote it in C. And he's going through all the C code here. This is what jlox code looks like. I'm just porting it to Rust so that I can learn Rust. All right, so, all of these need to be borrowed, right? Borrow, borrow, borrow. Oh. Okay, let's get rid of that comment. This has to be borrowed, and I probably need to clone it in order to avoid the... Okay, expected value, consider borrowing here. All right, and then these need to be borrowed. And these are probably going to complain about a temporary was created. Borrow. Nope, that didn't help. Borrow deref. And one of the things about Rust I'm learning is you just keep trying different things until you get it to work. Yeah, okay, so here we go. This is where our temporary is created, and then we try to use it after it's been dropped. So this is where we have to clone everything. And we're going to have to do that in the binary op as well, aren't we? So let's go down to the binary op and clone these guys. Yes, and now we have this issue with the immutable borrow versus the immutable borrow. Right, if we look here, it's can't borrow self is mutable. So this is the immutable borrow where we get a pointer to it, and then we try to mutate it here. So that's never going to work. Yeah, so one of the neat things, so Commander Thrashton says that, oh, they even implement a tracing garbage collector. Yeah, so if we look down here, next chapter is garbage collection. One of the things about Rust is it handles all that for you. So in C, yes, if you're writing C code, you have to write it with a garbage collector. But in Rust handles the memory for you and handles freeing allocations and frees for you, so you don't have to worry about that. So we get to skip that whole chapter. So this means, do I have to clone? Well, the self peak should give us a... Oh, now I can't borrow it, right? Commander Thrashton says, I thought it only handles reference counting. Yeah, so once the reference count drops to 0, then Rust knows, oh, I can free this piece of memory. That's the neat thing about the RCs, which I'm using everywhere in this code. And a ref cell allows you to modify data that's inside a ref or anywhere, but it's mostly this pattern here. You see RC, a reference count to a ref cell. Yeah, so we got a little bit further with this borrow. Now we can actually deref it, but now we still have the mutable borrow versus the immutable borrow. And it says it might be used here. While call is dropped. So what's a good way to work around this? I mean, I can just clone it, right? Just to solve that problem. But I don't like having to clone it. Hopefully I'm cloning the I'll have to do that here too. The ref count and not the, no, I'm cloning the value itself, aren't I? Yeah, okay. So after all of that exercise, we still have two. Oh, we're not using up values. Not using deref anymore there. All right, but now the bug was that we're printing out before when we should be printing out assigned. Let's see if that fixes it. And now, okay, so now it's fixed, but it's painfully fixed. Because we're cloning everything everywhere. Look at the diffs here. Not enclosure, native VM here. So whenever we want to use, where is it? I guess before we were doing a clone here for this. That's fine. And here we were doing a clone. But for our binary ops, where's binary ops? Yeah, so binary ops, before we were able to just pop the value off and then deref it to use it. But now we actually have to pop, borrow, clone, which is unfortunate. I wonder if I can say pop, because you pop it, you get an RC. Maybe I can clone it, clone the RC and then borrow. Let me try it the other way around and see if that works. Binary op. Here, let's try cloning the RC and then borrowing that. No, you can't do that because you're creating these temporary values when you borrow. If I clone the RC here, can I borrow in here? I can. Okay, that's good to know. So now I'm just cloning the reference count, not the whole value. But that means I can't do this. I have to do it this way. A.borrow, B.borrow. Yeah, okay. And let's just double check that that didn't break the assignment thing. It still says assign, that's good. So let's build release, right? And then I'll do my for loop that runs through all of the tests. Yeah, and there's no panics and everything looks good. Okay. All right. Good. Okay, so that refactoring is complete. Git commit -m fix bug, modifying or assigning, modifying a stack value through and up value wasn't working. All right. So with that in hand, now we can go all the way up here and start again with the last part of this section called closed up values. All right. Of course, a key feature of closures is that they hold on to a variable as long as needed, even after the function that declares the variable has returned. Here's another example that should work. But if you run it right now, who knows what it does? At runtime, it will end up reading a stack slot that no longer contains the closed over variable. If we do that in Rust, it should complain that that we tried to read past the end of the stack. Stack check. So let's try it. Cargo run. No, it's printing the word outside. So it didn't blow up. And it definitely didn't try to read a value that's not on the stack. Because it's right there. So maybe this is not the best example, or yeah, look at this. It isn't on the stack, but we must have put it in the up value. So, oh, wait a minute. So, I wonder if the way we implemented this, with the reference counting in Rust means we don't have to do any of this part of the chapter. Because automatically, if it gets popped off the stack, the up value still has a reference to it. So we don't have to do anything with it. Let's see. Global get set. Okay. The outer main function creates two closures and stores them in global variables so they outlive the execution of main itself. Okay, both of those closures capture the same variable A. The first closure assigns a new value to it, and the second closure reads the variable. What does the call to global get print? If closures capture values, then each closure gets its own copy of A, with the last value that A had at the point in time the closure's function declaration executed. The call to global set will modify set's copy of A, but get's copy will be unaffected. Thus, the call to global get will print initial. If closures close over variables, then get and set will both capture reference the same mutable variable. When set changes A, it changes the same A that get reads from. There's only one A. That in turn implies the global get will print updated. All right, well, let's see what our thing prints. It prints updated. Yeah. Which is it? The answer for jlox and most other languages I know with closures is the latter. Oh, good, because that's what we do now. Closures capture variables. You can think of them as capturing the place the value lives. This is important to keep in mind as we deal with closed over variables that are no longer on the stack. When a variable moves to the heap, we need to ensure that all closures capturing that variable retain a reference to its one new location. That way, when a variable is mutated, all closures see the change. So I think we've got that, because what's happening in our code is the stack now with this reference count thing. It's actually allocating on the heap, and the only thing that's getting allocated on the stack is the reference to the variable. So we don't actually have any variables on the stack at all. We just have references to them. We know that local variables always start out on the stack. This is faster unless our single pass compiler emit code before it discovers the variable has been captured. It's faster, yeah, but we're not doing that, right? And in fact, my initial thing didn't have it either. I had RCs everywhere. I didn't say stack value or vec value. Huh. We also know the closed over variables need to move to the heap if the closure outlives the function where the captured variable is declared. Following Lua, we'll use open up value to refer to an up value that points to a local variable still on the stack. When the variable moves to the heap, we are closing the up value, and the result is naturally a closed up value. So how would we do this here, right? I mean, the idea would be that the stack would just contain, I'm not going to make this change, but I'm just saying, for example, the stack would contain a vec of values. Actually, a vec of ref cell values, because we have to be able to modify it. And then the closure, instead of containing whatever the hell this is, it would be a ref cell of a vec of u size. Right, in Rust we'd have to do that because we won't have a pointer directly into the stack, but we can save the index of the entry in the stack. and then look up the stack variable. But we won't be able to do that with this because it looks like we're going to have to move it onto the heap, which means that this has to be a vec of, I don't know, struct, whatever. And it'll have a stack pointer, which would be usize, or a heap pointer, which would be an RC ref cell value. And then we'd have to figure out, oh, maybe it would be in enum stack. Nope. Usize versus heap. Right, and then that's what would go in here. It would be a vec of whatever. And that way we could use the enum to tell us whether or not to look on the stack for the thing and modify it there, or on the heap through this RC. And this has to be in a ref cell because we need to be able to modify the vec, adding things to it. And what else did we do? Yeah, we push to it, and then we look it up. I guess when we create the closure, we're doing this, so we might be able to get away with a little refactoring without having to put this in a ref cell. Okay, but that's beside the point. So this is what I'm thinking is this is the way this would work. Is what I'm reading here is we'd be able to either look upon the stack for a variable, or just copy it to the heap when we capture it. And so this would be the open up value. And this would be the closed up value. Where on the heap does the closure of a variable go? And Rust doesn't care. I mean, we don't care as Rust programmers because Rust will figure that out. When do we close the up value? That's the other thing. I don't want to do this refactoring because I just went through the whole pain of refactoring it into this. But maybe this is the right thing to do. Let's keep reading. The answer to the first question is easy. We already have a convenient object on the heap that represents a reference to a variable, the up value itself, right? The closure of a variable will move into a new field right inside the up value struct. And that would be just modifying that entry into a heap, right? That way we don't need to do any additional heap allocation to close an up value. What they're saying is that they would store the up value here. We would want it in a ref cell. No, in here, I guess, which is kind of what I'm doing. The second question is straightforward too. As long as the variable is on the stack, there may be code that refers to it there, and that code must work correctly. So the logical time to hoist the variable to the heap is as late as possible. If we move the local variable right when it goes out of scope, we are certain that no code after that point will try to access it from the stack. After the variable is out of scope, the compiler will have reported an error if any code tried to use it. By after here, I mean the lexical or textual sense, code past the closing brace for the block containing the declaration of the closure of a variable, right, is when that goes out of scope. The compiler already emits an op-pop instruction when a local variable goes out of scope. If a variable is captured by a closure, we will instead emit a different instruction to hoist that variable out of the stack and into its corresponding up value. To do that, the compiler needs to know which locals are closed over. The compiler already maintains an array of up value structs for each local variable in the function to track exactly that state. That array is good for answering which variables does this closure use, but it's poorly suited for answering does any function capture this local variable. In particular, once a compiler for some closure has finished, the compiler for the enclosing function whose variable has been captured no longer has access to any up value state. In other words, the compiler maintains pointers from up values to the locals they capture, but not in the other direction. So we first need to add some extra tracking inside the existing local struct so we can tell if a given local is captured by a closure. Yeah. But again, I think we don't need to do any of this. And I'm trying to think about, what about the performance implications? We still need to have a ref cell value here if we were going to make this change. If we make this change, we avoid having to go through the RC, right? So that saves us a level of indirection. With the up value array, we either have to say, oh, it's a stack thing, so then we need to go look it up on the VM, and the closure does not have access to the VM. So when we said get up value, we would actually have to return, oh, it's on the stack at this location, or here's we would have to return one of these guys. And then in our VM, we'd have to say, okay, if it's a stack, then look it up on the stack. If it's a heap, look it up on the, grab it out of the heap enum. But I don't see that as being any faster than what we've got already. So I'm going to undo that and undo that. And undo all that. Because I don't think we have to do any of this. But let's keep reading. So if it's, we'll set it to true if it's captured. Like this is slot 0 local. We don't have to worry about that. Ooh, later in the book, it will become possible for user to capture this variable. Okay. When resolving an identifier, if we can end up, that's probably going to be the this pointer, I guess. If we end up creating an up value for a local variable, we mark it as captured. And we can take a look at that in our compiler, where that is. Here's resolve up value. Right, so it's saying if we see it local, then this is where we would say it's captured locally. And then in end scope, now that at the end of the block scope, when the compiler emits code to free the stack slots for the locals, we can tell which ones need to get hoisted onto the heap. So we'll have a new instruction called close up value. I mean, we could do this and see it, but I think close up value is just going to be pop for us. I guess it couldn't hurt to add this in now in case it turns out to be important. The problem is here, of course. Compiler enclosing locals local is captured. We get the depth for local. We're borrowing this immutably. We can't modify it then in here mutably. So what's the right? If I tried this here, so it would be self-enclosing borrow mute. Oh, self-enclosing. I guess borrow, sure. And then it would have to say capture depth. And then write the function for the enclosing to set capture to true. I don't know if that'll work, but we can find out. Right? We can just write a capture here. Self. Oh, we don't. And then depth. Index is going to be usize. Doesn't return anything, and all we have to do is say. This would be locals. There it is, locals. It's a ref cell. Yeah, so we would say self. Oh. We have to modify the local. We can copy it then. Let new local equals self.locals.borrow of index. Make it modifiable. New local is captured true. And then I want to change, so I'd say let self locals borrow mute of index is equal to new local. Right? I don't know if that'll work. The first error is here. Oh, we didn't add, yeah, we have to add that to local. Struct local is captured. Cool. What's the next error? Oh, I have to unwrap it. As ref, unwrap. And then this is missing it, so it is captured false. Expected U size found U8, so depth as U size is captured false and is captured false. And now the error is move occurs. I guess we can clone it. And of course, clone doesn't exist on local. Probably copy too, right? No. Oh, okay, so that worked. Interesting. So we were able to modify the array this way and set that that way. And now we can actually see if close up value works. Because when we do the end scope, end compiler. Oh, end scope. No, right, that's right. So instead of just pushing a pop, we'll have to say if Oh, so yeah, I did it differently, didn't I? I changed this all. Is scope poppable? So I can say is captured. If self results borrow is captured, then we'll say emit byte close up value, else this, and now I'll have to write is captured. Which just says is the last one captured. Self locals borrow last unwrap is captured. And then I have to go over to the chunk and add this new opcode. And I ignored all of that other stuff about it, so I'm going to have to go back and take a look. 28 opcode close up value, and then in our disassembler, it's a simple instruction. Opcode close up value. So simple instruction op close up value offset. Okay, and then in our VM, we're going to need to handle it there. Oops, I forgot the comma. Opcode close up value is going to be something. I spell it right. Okay, so what are we going to do? Yeah, okay, so we didn't actually implement anything yet. But we can take a look and see what it does, right? By running that little piece of code. Pop, where's pop? We're going to do the same exact thing. So I'm just going to do this for now, like that. There. Let's run that global get set and see if we get anything like that. Do we see a close? Nope, there's no close up value there. So what kind of code would actually do that? Let me print out when we capture something, and that way we can see capturing. Oh, okay. I can just, all I have is the index, but I can print that out. Capturing index. All right, and then just do this through less and see if we get that. Yeah, so capturing index 1. So that should have, when we ran the script, index 1 is var a. So when we ran the script, we should have seen that. So here's where we're starting the run. We have the script. Op nil. Defining to global. I'm not sure what this, this line 1 is here. Okay. Line 2, we define global get, we define global set. Okay, and then we create the closure. We call closure on main. We define global, get global, call constant closure. It's doing a pop. So I don't know if my code's working right, because we should be seeing right, if I look here for the set function, when we call set, it should capture this. And where do we call set? It's right here, line 15. So we should see, instruction 15, which happens to be line 15. So here's where we call it. We set up value, and then we pop. It says capturing index 1 for get, right? Or for the set. I'm confused because I would have thought that we would have seen when we ended the scope of set, we should see that. I mean, it's printing out the right value, but okay. Let's see if he has another example where this actually gets used. Let's move over to the runtime side. Before we can interpret op close up value instructions, we have an issue to resolve. Earlier when I talked about whether closures capture variables or values, I said it was important that if multiple closures access the same variable, that they end up with a reference to the exact same storage location in memory. That way, if one closure writes to a variable, the other closure sees the change. Right now, if two closures capture the same local variable, the VM creates a separate up value for each one. The necessary sharing is missing. When we move the variable off the stack, if we move it into only one of the up values, the other up value will have an orphaned value. To fix that, whenever the VM needs an up value that captures a particular local variable slot, we will first search for an existing up value pointing to that slot. If found, we reuse that. The challenge is that all the previous created up values are squirreled away inside the up value arrays of the various closures. Those closures could be anywhere in the VM's memory. First step is to give the VM its own list of all the open up values that point to variables still on the stack. Searching a list each time the VM needs an up value sounds like it might be slow, but in practice, it's not bad. The number of variables on the stack that actually get closed over tends to be small, and function declarations that create closures are rarely on performance-critical execution paths in the user's program. Closures are frequently invoked inside hot loops. Think about the closures passed to typical higher-order functions on collections like map and filter. That should be fast, but the function declaration that creates the closure happens only once and is usually outside of the loop. So it looks like we're going to just add to the up value a pointer. So every time we create a new up value, we'll just link them all together. And that's in the C version. Starting with the first up value pointed to by the VM, each open up value points to the next open up value that references, right. So I'm just looking here as a next pointer. It starts out as null. The VM contains a list of all the pointers to them, and it can walk the chain. The chain starts out as null. And yeah, so next just keeps pointing back. So when we capture an up value, we can keep a list of them. But like I said, we're reference counting it, so I don't think we have to do this. Let me see, is there an example anywhere here? No, there's no example. So I can't test out this code to see if it's working, it's doing the right thing. I mean, he has an example here, but doesn't get used. Right? I mean, nothing gets called. Let's see what compiles as a result. We can take it, even though it won't run. I mean, nothing will happen to run it. We can still look at the assembly that gets generated. Yeah, so this says capturing index 3, capturing index 5. But we're not printing out I guess because we're printing it, we don't need a pop instruction for it. Here's close-up value. Okay. So when we start executing here, we're actually executing the block, right? We create a constant 1. We create the closure for function f, which has a local variable. This a is the local variable. It's local to the scope of this function. That's why it says local, right? We have a constant 2. We don't actually call the function. We just create it, right? And then we do this line here. Var b is 2. And then we have var c is 3. So this is 1, 2, 3, 4, 5, right? And that's why these things are what they are, right? And then h, here's h, and then we pop close-up value, because I guess we knew that we needed to. And that's it. Oh, Justos. How are you? I missed your message earlier. So I think we're done. Git status. Diff. I mean, we're just emulating the close-up value just to ensure that we can actually do it in case we need to be able to do it for a future chapter. Okay, well, that's fine. We get all this for free. We get a bunch of stuff in Rust for free. Like, for example, we didn't have to write our own hash map code. Git add source. What's Clippy have to say about all this? Ooh, Oh, good. I can remove some clones. I should have checked with Clippy before I did the other thing. But that's from the previous thing. Okay, so let's add this. Section 25.4 closed up values. Do we really need this? And then I'll fix all these Clippy things. So yeah, if I can remove clones, that'd be good. Cargo Clippy. Let's start from here. 341. This value is dropped without further use. It is. So I can do this. And then down here too. Yeah, look at that. That makes me feel better that I don't need to clone things. Yeah. Okay. Git add source, git commit -m, remove clone calls from pop values. Okay. Let's push that up. Take a look here real quick. There we go. And then what I want to do is see if I can fix a couple more things, because the next thing is garbage collection, and I'm going to skim this tomorrow or whenever my next stream is, hopefully tomorrow, but I don't know. Sometimes I miss a day. And we can skim over this, but we're not going to actually do any of this because we don't need to. The next chapter we actually need to do is classes and instances. So let me go back here. Yeah, this is something I want to work on. And take a look here. We have 7 problems in our jlox AST code, and I want to see if I can fix all of them. We're so close to getting this to pass the test suite. So this is the first one that fails. So Java, right. And then I was able to do this and just paste this in here. This is what the output should look like. Oh, right, we were having a problem with this. Trying to get these 2 errors to come out at the same time. All right, I'm going to ignore that one for now because that's painful. Let me at least get these guys working, right? These are equals method. It should be printing out true then false, and in our code, what are we printing? How do I run my test? Jlox AST, target release, oops, target release, jlox AST with this test. And I'm printing false, false. So, does foo equals, oh, okay. So let's take a look at how we handle equality. I forgot all of this code. It's been too long. Would it be in object where we compare equality? Oh, I see. We're deriving partial equal. So if we look at the interpreter, visit get, visit set. Is truthy right? I'm trying to remember how this all worked. Here's our quality checking. Oh, okay, yeah. So we have a number or a number on the left and right. We have bools, we have nils, and anything that's different we get. Oh, interesting. Oh, I said here it's automatically false. If we're comparing anything else, it's automatically false. So we could do object What's the object type? It's function. And that'll give us a lox function. We can just compare the pointers, right? Func A, object func B, and we can just say it returns object bool rc pointer eq ab. Can we do that? Will that work? Didn't like that. Oh, because I put a capital B in there. Oh, okay, I can borrow those guys. Good, okay, so let's see now, do we print out true, false? We do. Okay, so that should fix that test. We also have equals class, so that's going to be the same problem, right? We need to be able to check class equality. And so let's go back to object, and what are we looking at here? Just class, and class is also an RC. So we can, we can just copy paste this and do class. And then run this. That. All right, hopefully that's correct. True, false, false, true, false, 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 false. Perfect. And what else? So that's that one. Add bool num. What is that one doing? Expect runtime error. Operands must be 2 numbers or 2 strings. So if we run ours on that, what do we get? Operands must be numbers. Oh. Yeah, I'm just saying arithmetic error here. I guess I could change this up a little bit, right? If I make this a token type plus, is that going to break everything? Break other tests? Yeah. So okay, now we have that error. All right, so let's run the Dart test again and see what. Okay, so we're down to 4 errors. And now we have not equals tests. What is this supposed to be doing? False, false, true, false, true, false, true, 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 true. And what does our wonderful little code do? Oh, operands must be numbers. On line 14. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This last one. Really? I guess that's this error here, right? Oh, I have it different, right? Yeah, I have the num and string thing. So if we're doing a num string, I have a plus, but the not equals should give us a true. And the same with string num. Right, so that's basically these 2 lines. I'm not liking the way this is turning out, but okay. Let's do that, and hopefully that does this. Let's see what happens here. Okay, false, false, true, false, true, false, true, true, true. Okay, and this equals, let's see. We have true, true, false, true, false, true, false, false. Okay, so let's take a look at Dart again. So just these two guys. And this is, both of these are thing in which, where's my Java? We actually get multiple errors because it keeps parsing, right? So that's a statement condition, and this is a statement initializer. So on line 3, it's saying expecting an open brace, expect expression, and then error at close paren, expect semicolon. So it's the same issue. And if we look at the code, right, for both of these, we can see basically we stuck a block inside the for loop, or a block here inside the for loop. And what's happening in the reference implementation is we see the open brace and say, no, we expect an expression, but then we keep going and then see the semicolon. Oh, sorry, the close paren, and say, oh, wait, we're expecting to parse an expression. So this turned out to look like an expression, right? Just a is less than 2, and then it just threw it away. And here's a is a plus 1, and it's saying, okay, we need a semicolon after it, and there isn't one. The same with this guy, where it parsed this, and then it saw that and says nope, and then it continued to the next semicolon. So maybe that's the synchronize point. Oh, it's in parser, right? Or we synchronize. And it may be that the synchronization needs, self previous is a semicolon and return. So it is supposed to do this. So maybe that, and it's just happening inside the for. So it could be our for loop, because the for loop is a desugared while loop. Right, I think we were looking at this before. What's happening is we're getting this early abort. And what we should be doing, so where does for statement get called? Maybe we need to be doing a synchronize after a for statement if the for statement fails. Let's take a look at his for statement. Let's go up. And I guess it's under control flow, right? For loops, yeah. Okay, so do we try to synchronize after the for statement? This is inside for statement. Yeah, this is just saying match for return statement. Oh, maybe we're returning like a false. No, it just says return for statement. Okay. I'm just scanning all of this code here bit by bit, and I don't see how it's doing the double error. Is there a synchronize in here? There's no synchronize in this chapter. Is there one in here? Yeah, we call synchronize. And where do we call synchronize? Oh, we call it whenever the declaration. Okay, so let's take a look at declaration. Yeah, if result is error, then we synchronize. Let's print that out. And see if we actually see that, because it feels like we're not. Right, here's this statement. So let's take a look. Where else do we call synchronize? Right, that's the var declaration. That's over here. Right. That's that. Okay, and then on the next one we don't do any sync. In functions we don't do a sync. Yeah, so we didn't add anything new for that. Okay. So we should see the synchronizing statement. What am I doing? I want this one here. It says synchronizing. Right? And then after it finishes so synchronizing must be going too far. Let's watch the synchronization happen. We self-advance. And if we're not at the end, then we'll check the previous token type. So maybe we can print that out. Sync debug this self previous. Can we do that? Yes, we can. Okay, so let's take a look at what that does. It's synced on the semicolon. Right? And so then it should start parsing right here. Oh, maybe do I stop? Oh, do I stop parsing if I get an error? Oh, maybe that's the problem. Maybe that's the problem. Because if declaration fails, right? Who calls declaration? Yeah. I'm doing a question mark here, and what I should do is just keep going until we reach the end. So if let OK D equals self declaration, self push D. All right. Now let's run this again. Okay, but we didn't see the... Oh, we did. We got it. We got it. That worked. Okay, so let's get rid of those debug statements. Nope, I gotta wait for it to finish building there. And then the other one was statement condition. Nice. Okay, does Dart work now? Oh, of course, everything's broken. Everything's broken because now we're reporting multiple errors. So let's take a look at the Java version for this. Let's the output of the Java version for the var in then is this, and for us it's the same thing. So what's it complaining about? Expected return code 65 and got 0. Okay, so we still need to return. Okay, so that's the last bug to fix then, is hopefully. I shouldn't be so confident. So error locks result fail. The thing it calls parse is our main, right? Yeah, parser parse. This returns lock result fail. And where's run called? Run file. Oh, I'm doing it 70. Oh no, it's doing standard process. It's saying okay. thinks it's okay. Oh, is that because I'm not reporting the error? Here, we're never, no, this is saying, it's reporting the error here, right? So it should be setting, where's our error? Here it is. Self-had error is true. Maybe it's... Yeah, synchronize itself doesn't set that, but... Okay, let's take a look at that fail again. We call it jlox result fail if we had an error. The only way we have an error is if we call the parser's error method. Right, and so where is that called? Self error. Invalid assignment target. So what we should be doing here for all these expect expressions is not calling jlox result parse error. We should be calling error. Oops. Like that. Okay. And now if I run this, we get error 65. So let's do the Dart. Oh my God. Didn't we just fix this? Okay, and the Java version looks like... Oh, that's the difference. Value versus expression. Did I have that and not realize it? Yes. I'm expecting after expression. I have after value. Let's take a look at that. Expect semicolon after loop condition, after value. Oh. Yeah, so this should be expression, right? This is after return variable, after variable declaration. Expression statement should be after expression. Okay. Let's see if that breaks other things. So let's run ours. Now it works. Dart. Aha! Finally! Okay. Great news. All 239 tests pass. Out of 556, I guess. Okay. Oh, 556 expectations. We did skip a bunch of tests though, because those tests aren't relevant for jlox. If we pipe this through less, we can see all the ones that are skipped. Too many constants, for example. We don't have that issue in jlox, but we do have it in clox. And so we will see that error. That's probably a big file, isn't it? Yeah, so this creates 256 constants, and that should fail using clox. In fact, we should be able to do that, right? Unlocks bytecode, target, debug, unlocks bytecode with that file. Error at oops, too many constants in one chunks. Okay, I have to fix the oops. Oh no, that's correct. We are supposed to say oops. Oh, I see. It's at oops because that's 256 and then blam, there's 257. Okay. Cool. All right, so at least that part of locks. I wonder if we can dart that guy. Let me build this release with no default features. I'm just curious now. See how far we got with the C version of this. So this should be test dart jlox, and the interpreter is lox bytecode target release lox bytecode. Wow. We are passing 106 tests though. All right, so this is good news. Let's check in with Clippy. Clippy's happy, get diff. I have a bunch of things that did things. Okay, git status, git add source, git commit, and update fixed code to comply. Yeah, with test suite. Git push. All right, so let's go back here just to be happy. Zoom. I don't know if you saw it really quickly. It said 15 tests that were skipped. All right, that's my stream for today. Tomorrow, or whenever my next stream is going to be, we'll skim over the garbage collection chapter and then start looking at actually, I really want to start looking at cross-term and building my own text editor. This is in C, and I want to port it to Rust because I want to learn cross-term. So maybe this is going to be my next stream. I haven't decided yet. Anyway, that's where things stand for now. Thanks for hanging out with me, everyone, and I will see you next time. Take care.